All right, today we are going to talk about parameter estimation. The first question in your guided questions is about why you think it is called parameter estimation rather than something like parameter identification or parameter determination. So make sure you answer that question before we get started with the rest of this lecture. So parameter estimation is the process by which we are going to estimate our parameters, just like it says. And our parameters are often what we've been calling K, subscript something, K1, K2, KR, anything like that. That's pretty much what we've been calling our parameters in this course thus far. And so in your system of equations for the SIR model, you have two parameters. The first governs the infection rate, so that we're going to call Ki. So, and then the other governs the recovery rate, and we will call that Kr. So the things that we are focusing on estimating is Ki and Kr. So early in the case study, in fact, in the pre-case study assignment, you got some set of data related to your particular epidemic or pandemic that showed the number of either deaths or infections or illness cases. Over time, which was in weeks. And every group had slightly different data, but everyone's data mostly followed some case where it went up and then back down. And so you want to fit the goal of parameter estimation here is to fit the model that we already wrote to this data. And hopefully what we will get will be some type of estimated curve. Can't pick a color. Some type of estimated curve that roughly follows that shape. It almost certainly will not be perfect because real data is never quite as smooth as the simulated model data. And so in this example, since we were looking at deaths or infections, we want to fit dIdt to our data. Since deaths are going to be proportional to infections, or infections or reported infections are going to be proportional to total infections. In no case is the data exactly going to perfectly reflect all of the infections in the population. There's always going to be some people who got the influenza that you are studying who didn't die or didn't report their infection to a doctor or didn't have their infection laboratory confirmed. So we're really looking at the shape of the DI/DT curve rather than necessarily the exact numbers. So just to kind of write out the goal here, we want to match the shape of the infections to the observed data. So in order to do parameter estimation, we need to have some sort of score function. Make score function pink. No, that seems like it might be too close to red. We'll do score function as purple. So we'll have some sort of score function. And that will define kind of how close our experimental data is to the simulated data. So this point is right on it. This point maybe a little off the center. This point's quite a bit off relatively. And so the score function is calculating the difference between the simulated data and the observed data. And so your score function should reflect whatever it is you are really trying to compare. And so I want you to think about for question 3, what some of the key considerations you think should be for the design of a score function. And then I want you to consider for your own model what things you're going to need to consider when designing a score function. For example, what parameters are you going to estimate? And we already went over that. And then what exactly are you going to compare DI/DT to make sure that what you are fitting to is the shape of the observed data. We'll discuss this some more in class, and I will see you then.